All right, let's take a look at today's lesson. We're going to be looking at linear approximations today. That's what we're going to be looking at. And what is that? What is a linear approximation? And also another word for it, you might also see this word, is local linearity. So linear approximations, or the other vocab word would be local linearity. What is that? That basically tells us the tangent line of the function at a particular value can give you an approximation of the y value close to that. So I know that's a lot of math words. Let's look at the diagram, the graph. So literally what we're talking about is we're going to find the equation of the tangent line. These are the steps we're going to take. We're going to find the equation of the tangent line. So that's our step one. Then step two is we will use this tangent line equation to approximate a function value. And what I mean by function value is y value. Okay, so in this picture that I have drawn right here, so let me go through the steps again. So step one, we would find the equation of the tangent line. Step two, we're going to use this tangent line equation to approximate the function's y value. All right, so for example, let's say we find this tangent line equation in red. And let's say that I want to know this value, this y value. Notice it's on the curve, on the black curve. I want to know this y value. Well, what would I do? According to this technique, what I would do is I would actually get the y value from the tangent line and use it. Let's get it a different color. So we would get the y value of the tangent line, and we would use it to approximate the y value on the function. See how close those are? They're very close. It's a pretty good approximation, as close. We need to be close. So our goal is to be close to the point of tangency. So this is the point of tangency. We want, because as close as you get to the point of tangency, the better your approximation is. What if I wanted to, let's say I wanted to, I don't know, let's say I wanted to approximate this y value with that y value. I mean, is that going to be a good, and those aren't showing up very clear. Let's say I want to approximate this y value with this y value. Would that be a good approximation? Not really, right? Look at the space between here. I mean, that's a lot of space between there. So that's why what they will typically do for us is they will give us points that are very close. We want to be very close to the point of tangency. Those are much better approximations. But that's our job in this lesson, is to find the equation of the tangent line and use it to approximate a y value on the function. Okay, does that make sense? Okay, so let's look. We have a few examples where we do this, and hopefully by the end of these examples, it will be okay and make sense to you. So let's see. We've got f is concave up on its domain. Now we don't really know what we need this for yet, so I'm just going to highlight it. We're going to need it, or they probably wouldn't tell it to us. So we'll just put that on hold. And they give us function values. So they tell us f of 4 is 5 and f prime of 4 is 3. So we want to use the local linear approximation. What does that mean? Those are fancy words for tangent line. That's all that means. Local linear approximation is tangent line. We want to use the tangent line for f at x equals 3. Which is, all this data that we got here. That's why they gave us all of that information, so that we could write the tangent line at 4. This is where our tangent line is going to be at 4. Okay? So, just remind us, so it's y y minus y1 equals m times x minus x1, my favorite equation of a line. So we're going to insert so this is our x value, and this is our y value, and this is our slope, right? So x is the 4, y is the 5, and m is the 3. That's our slope. F prime of 4 is 3. So let's fill in those locations. So y minus 5 equals 3 times x minus 4. So that is my tangent line. Okay, so this is my tangent line. Okay, so what do I want to do with my tangent line? I want to estimate f of 3.8. Well, it's good they're giving us that information. We don't even know what the function is. We have no idea what the function is. So this is one way that they kind of force us to do this kind of an approximation where we don't even know what the function is. All right, so what are we going to do? What we're going to do is we're going to take this number, okay, this number right here, that 3.8, and we're going to put it right here where the x is. That's how we use that tangent line to approximate. We substitute the value, the x value in for x for the y we want to approximate. Okay, I'll say that one more time. We substitute the x value in to approximate the y value of, f of 3.8 is the y value at 3.8. All right, so let's do that. So we have y, and I'm going to move the 5 over. I hope that's okay with you. It's minus 5, so it's going to be a plus 5 over here. Plus 3 times, so it's going to be 3.8 minus 4. Typically, this kind of calculation is pretty easy. We won't have a lot of crazy stuff going on. I mean, 3.8 minus 4 is like, what, negative 0.2? So y is 5 plus 3 times negative 0.2. I multiply 0.2 times 3. I get 5 minus 0.6, which gives me what? 5 minus 0.6 would be what? 4.4. So f of, and we need to rewrite it in the words that they use, f of 3.8 is approximately 4.4. And that's our very first linear approximation. How are we feeling about that? Are we okay with the linear approximation? Okay, that's what we do every single time. We find the tangent line, then we plug in the value we want to approximate. Okay, one other little nuance for this, and this is talking about over and under estimate. In order to do this over or under estimate, you have to know about concavity. So this part right here, this concave up business goes down here. It's going to be an over or an underestimate, and we're going to talk about how we can tell. So what we want to do is we want to think about what would a concave up function look like. So I'm going to draw a picture. So I'm going to draw a picture of a concave up function. This is concave up. Okay? And what would our tangent line? So we found a tangent line. Where would our tangent line go? Would it go here, like underneath it, or would it go above it? I mean, it's going to go underneath it. That's the only place to put it, right? We can't go above the curve. So this tangent line, the tangent line is below the curve of f. Okay, we're going to call that curve f. The tangent line is below the curve of f. So that means every y value on the tangent line is smaller or below the y values on the curve. Does that make sense? We can physically see them. All of these little y values right here, all of the little y values are all smaller than the function value. Therefore, our approximation is going to be an underestimate, we're explaining, is an underestimate because f is concave up, and we're going to repeat the words back they gave to us, concave up on its domain. So that's how we explain whether it's an under and over estimate, is we talk about the concavity of F. Okay, are we all right? Is that comfortable? Okay, we have two more examples, very similar to this one, just more practice. All right, so let's look at this one. Here they actually gave us a function. That's nice. All right, so we have that function. We are told it's concave down. We're going to need that later, right? What are we going to need the concavity for? Over or under estimate, right? That's what we need it for, over or under estimate. So we want to find the tangent line at x equals 1. So I'm writing my favorite equation of my line, y minus y1 equals m times x minus x1. Okay, so this is x1 right here. That goes there. So what spots do I need to fill? I need to fill that spot and this spot. Those are the three spots I always fill for tangent lines, right? I need those three values. I have one of the three already. To find the y value, what do you think I'm going to do to find the y value? I'm going to plug the x value where? Into the original. So I'm just going to do that work over here. So f of 1, that's my x value. I need to find the y value. F of 1 is going to be 5 times 1 minus 2 times 1 cubed minus 2. Let's see, what is that? So, oh, y'all know how I am with arithmetic. So we've got 5 minus 2 minus 2. All right, so what is that? 1. Okay, so let's just start building our equation. So 1 is going to go here. Okay, I don't know what m is yet. Okay, so I'm just filling in the parts that I know. I know x1 and y1 now. How am I going to find the slope? What do I need to do to find the slope? I need to find the derivative, right? I need to find the derivative. So f prime of x, so we just use our power rule. That's kind of nice, right? Just the power rule after we've learned all the other fun rules, product rule, quotient rule, chain rule. Yeah, power rule is kind of nice. So the derivative of 5x is 5. The derivative of negative 2x cubed, let's see, what would that be? Negative 6x squared. And the derivative of negative 2 is 0. And we want what value from the derivative? We want the value at x equals 1. We want that value. So f prime of 1. So 5 minus 6 times 1 squared. Let's see, what does that give me? Negative 1. So that's my slope. So there's my tangent line. And that's what it asked me to do. It simply asked me to find the tangent line. So there we go. We're good. I really highly encourage you to leave it like that. Please don't distribute and combine like terms. Just leave it in point slope form. There is really no reason to distribute and combine like terms unless it's a multiple choice problem, and that's how the answers are written. Otherwise, please leave it alone. Now, they want us to estimate what is the estimate for f of 1.1 we're using the local linear approximation for f at 1. What does that mean? That means we're using this tangent line at 1. That's what all those math words mean. That we're using the tangent line at 1, just fancy words that say, hey, use the tangent line at 1. Okay, we can do that. So y minus 1 equals negative 1 times. We're going to substitute in the 1.1. So what do we have? And I'm going to move this 1 over. So it'd be positive times, let's see, 1.1 minus 1 would be what, 0.1? Right, that sounds right. Okay, and so 1 minus 0.1, what would that be? 0.9. So f of 1.1 is about 0.9. So there's my approximation. Okay, are we okay? Okay, so we've written our tangent line. Now we've estimated using the tangent line. Our last task is it an under or over estimate? Explain. What information do we need to know to determine whether it's an under or an over estimate? Concavity. We need to know whether it's concave up or concave down. So this one is concave down. So let's draw that picture. Okay, let's look and see what that looks like. So this is like concave down, right? My tangent line would look like this. So the since F is concave down, the tangent line is above F. Okay, see how it's concave down, the tangent line is above it? So what does that mean for us? That means that for every point, every y value on the tangent line, all those y values are going to be what? Are they going to be bigger or smaller than the y values on the function? Bigger. They're going to be bigger. These are going to be bigger. That means that this is an overestimate. So we would say our explanation would be overestimate because F is concave down, and they tell us from 0 to infinity. You really need to write that. Please don't just say concave down, from 0 to infinity, and the estimate is at x equals 1. Okay, that's why we can say, what if our estimate was at x equals -1? We wouldn't know anything about the concavity, right? We wouldn't be able to say whether it was an over or underestimate. Okay, you with me? Or we'd have to find out what the concavity was. So the concavity, this interval includes this where we're estimating. We're estimating at 1.1, and that is inside the interval of 0 to infinity, which is why we need to actually write that down. Okay, we need to really write that down. Okay, are we okay? All right, one more. One more. So now we have a differential equation, which is a fancy word for a derivative. Okay, this is a differential equation, just means derivative. This is it. Okay, so differential equation means derivative. We have a derivative. Let y equals f of x be the particular solution to the differential equation. Those are words that they just mean the solution, right, is like the position. That's all that means. Solution is like position with the initial condition of. So this is a point on the curve of f. That's a point on the curve of f. That's what that is. Write an equation for the line tangent to the graph of f at the point 2, 0. Okay, so y minus y1 equals m times x minus x1. And we need x1 and y1 and m. Okay, well, we've got, this is x, and this is y. So y minus 0 equals, we don't have m yet. Okay, but we have x and y. Now, how are we going to find the slope? Where do we get slopes from? We get them from the derivative, right? So I've got a little bit of work to do over here. Not too bad. So I need dy dx. I need that value at 2, 0. That's what I need. So I'm simply going to substitute in, this is my x value, that's my y value. I'm going to just put those in the derivative and calculate it out, see what my number is. So I've got e to the 0 times 2 times 2 squared minus 5 times 2. Okay, I just substituted into the derivative. We know e to the 0 is 1. So 2 times 2 is 4. 4 times 2 is 8. 8 minus 10. Okay, I'm getting -2. Does that look right to y'all? Is my arithmetic okay? That's -2, right? So there we go. So yay, we wrote the equation for the tangent line. Done. Now, do you have to put the 0 there? No, you don't have to, but I just don't want to erase it. So you can do it just like that. Okay, great. Questions on that? Okay, then the second part is use the tangent line to approximate f of 2.2. So what are they asking us to do? They're asking us to take at 2.2 and they're asking us to put it right here. That's what they want us to do. We're using the tangent line to approximate that function value, that y value. Okay? So let's do that. So we've got y minus 0 equals negative 2 times 2.2 minus 2. Let's see, what is that? So y is negative 2 times, let's see, 2.2 minus 2, that would be 0.2, right? Yeah, so negative 2 times 0.2 is negative 0.4. So we'll rewrite with their notation. F of 2.2 is approximately negative 0.4. Oops, let me fix that, negative 0.4. Okay, how is that?